Hi, everybody. Hey, were you able to see the recordings now that I put them on YouTube? Oh, good, great. So, small miracle. Okay, so let me start. Remember last scene, we were looking at structured connectivity, in particular Hopfield networks. So Hopfield networks. No, these are a model for associative memory. And the picture we have is basically, this is activity space, R1, R2, R3. So activity space. So we use S, and the idea is there are many fixed points. Okay. And each of these fixed points corresponds to a memory. So activity space, multiple fixed points. And each point corresponds to memory. Put memory in quotes, but maybe memory shouldn't be in quotes. I mean, we really think of this as memory is associated with some activation of neural activity, and associative networks, associative memory, you can recall a memory by just remembering a part of it. And so the equations we use, so classic Hopfield model, I'll give you the references to these papers on the website. I believe this was a 1982 paper, but to give you the reference, the update rule was SI of t plus 1 equals sine of 1 over n, the sum on j of jij sj of t, and jij was sum on mu of squiggle I mu, squiggle j mu, and these are random variables. Squiggle I mu equals +1 with probability 1/2, and -1 is the probability 1/2. And so what's really important to realize is that there we go. So the weights are chosen, or the memories, so the squiggles, so these memories, which are squiggle I mu, chosen ahead of time. And then fixed. Okay. Now the memories are pulled from some random distribution. So these memories, in some sense, is a noise process, and this is known as quench noise. So quench noise. Okay, because these squiggles are just random variables, but once they pick, you stick with them as you run the network. Okay, and it's very important that they're uncorrelated. We won't go into that, but it's kind of in these Hopfield networks, you have to take a memory and code it into an uncorrelated variables. And the reason we call these memories is because remember, these squiggle IMUs are fixed points of the dynamics if n is not so large. Okay, and we need, remember, there are p of these memories. So the relevant numbers, there's p memories, and actually I'm going to use capital N, and there are n neurons. Okay, and then in this really simple model, that's all that matters is p and n. Okay, if p is not so big compared to n, these squiggles are fixed points, and you can think of them as memories. Okay, as I pointed out last time, there are several problems with this model. One is this dynamics here doesn't look anything, doesn't really look like neurons. Neurons have some memory potential, they emit spikes. So you can kind of think as SI of t, you can think of 0 for no spike and 1 for spike, but it doesn't quite make sense, or -1 for quiet, 1 for spiking. It doesn't quite make sense because then every other time step it spikes. So these don't really look like neural dynamics. This doesn't look like a real neural network. There's no voltage, there's no spikes. Time is discrete. I'll put that down. So no voltage, no spikes. Time is discrete. Also, there's no background state. It's always, so each fixed point corresponds to memory. To a memory, which is not really ideal. You don't want to always have to remember something. You want to be able to have some, just think about nothing, for instance. And finally, we use all-to-all connectivity. So this last one is kind of important. So the reason this is important is, remember, number of memories you can get without the whole thing falling apart is proportional to n. And it's p, it's got to be less than 0.138 n. A super famous number. I'll give you that reference too, but it's a really hard paper to read. If you want a lot of memories, so a lot of memories implies n is large. Say, let's say 10 to the 6. Let's say 10 to the 7. That'd be kind of nice, right? So you have 10 million neurons. Now you can remember on the order of 10, 1, 13% of that. So order of 1.3 million things you can store easily, a couple 100,000, which is plenty. But if you look at, remember, if you look at the equations, Jij is all to all. So Jij, every neuron connects to every other neuron. Okay, and you can't have So neurons can't connect to to 10 to the 7th other neurons. So neurons connect to about 1,000. Okay. So what the first thing we want to know, the absolute first thing we're going to ask is, so what's the capacity is kind of jargon for number of memories when each neuron connects to only okay, it's the first we're going to ask. We're going to say, okay, what we're going to do is make this network steadily more realistic. First, we're going to consider all-to-all connectivity. Then we're going to make it continuous time, and finally, we're going to add a background. And each time we do that, as we'll see, well, actually, the only really thing that hurts capacity is the first thing we do. Okay, getting rid of all-to-all connectivity, that's really what kills you when it comes to capacity. The other ones don't really, there's not much yet. Okay, the first thing we're going to do now is consider the same network as before. So again, SI of t plus 1 equals SI of t, actually, sorry. Sine so the exact same structure to the network, sum on J, oops. Sum on J, Jij, Sj of t. However, for Ji, and Jij is going to be kind of similar. Sum on mu of squiggle I mu, squiggle J mu. But we're going to put this Cij in front, and Cij equals 1 with probability k over n, and 0 with probability 1 minus k over n. And you know, this prefactor doesn't matter because we're taking the sign, but it's sort of convenient for what we'll do later. We'll actually put 1 over k here, because there are now k non-zero terms in the sum. Okay, so what this means is each neuron connects to, instead of all n neurons, so this sum is j equals 1 to n. But because of this Cij term, only about k terms in that sum are non-zero. Okay, the Cij just blanks out most of these terms if n is large. Okay, so we want to do the same analysis before. We're going to ask, so Si equals squiggle I mu. So our guess, and we're going to ask if that's still a fixed point of the dynamics. Okay, so we have squiggle I mu, and the same thing as before. It's a little bit harder. We'll put a question mark here because we don't know. Sine of 1 over k sum on j. So first of all, we have a Cij, and we have a sum on mu, or sum on nu, of squiggle I nu, squiggle j nu, and we're going to put squiggle j mu. So in this step, all we've done is we've set SI of t equal to squiggle I mu. Okay, that's our guess. So as before, we separate out terms. That equals sine of 1 over k. Well, first we'll separate the nu equals mu term. So we have sum on j, oops. Sum on j of Cij squiggle I mu squiggle j mu squiggle j mu. And this, of course, is 1 plus 1 over k, the sum nu not equal to mu, sum on j of Cij squiggle I nu squiggle j nu squiggle j mu. Okay, so we have two terms to deal with. This term is equal to squiggle I mu times 1 over k, the sum on j of Cij. Okay, that's because this term is identically 1, which is convenient. And this quantity here, so this term is approximately equal to 1. So Cij, remember, see the Cij is 1 with probability k over n, and 0 with probability, and 1 minus k over n. So approximately k terms in this sum are 1. We can work out, it's plus or minus 1 over k, but we don't really care so much about that. This is random fluctuations around the mean. But it's k is large, but we'll put that in. So now we just have to deal with this term, okay? So for that, I'm going to go to the next page. Oops. So I have 1 over k, 1 over k, the sum mu not equal to nu, the sum on j, Cij, squiggle I nu, squiggle j nu, squiggle j mu. Okay, so what do we have? We have, so the number of terms in the sum, so there are p minus 1 terms from the sum on mu, and there are approximately k terms. So approximately k terms in the sum on j. Okay. And each of these things is either plus or minus 1. Okay. So this whole sum is 1 over k times the square root of p minus 1 times k, and then times some random variable. So 0 mean unit of variance. It happens to be Gaussian, but we don't really care about that. Okay. And that's something I went over last time. It's super, super important that you know where that comes from. Okay. So this is approximately equal to the square root of p over k. So p is large enough so we can ignore minus 1, p over k, eta I. So we have a following picture that's very similar to what we had last time. So if we plot here sort of S space, so this is -1, and this is +1. Okay. And if we look at what goes inside this sign, there's a squiggle I mu times something that's about 1, and this noise term, which has some spread. So basically, for different values of I, what we're going to get is spread around here and spread around here. But the width of these things is square root of P over K. So remember, in the previous all-to-all conductivity was square root of P over N, now it's square root of P over K. So, so if we want squiggle I mu to be a solution, so I need P much less than K. Okay. So this may have been kind of fast. So let me just go over and recap. So this is our setup. Okay. We're going to put this Cij in here that gives us sparse connectivity. It's 1 with probably K over N and 0 with probably 1 minus K over N, which means there are basically only a fraction of K over N in terms in the sum are non-zero. So in this terms in the weights are non-zero. So in this sum over J, there are only about K, each neuron gets input from only about K others, not N others, okay? For 1 minus N over K, this thing is just 0. So we take this model for J and we plug it in here and break up the mu equals, this is nu equals mu, and that just gets us our squiggle I mu back, okay? And then all the other terms are random and give us some effective noise. So each different I, we get a different value here. So that's actually maybe worth writing down. What we end up with is squiggle I mu equals some question mark sine of squiggle I mu plus some noise A to I mu. And this A to I mu, that's a distribution here. It's a distribution of A to I mu. Okay. And that distribution is with respect to this index I. Okay. Every time there's different I, this comes out to be a different number. And what we don't want is for this I, this distribution to be large enough so it leaks over here. And when squiggle I mu is 1, this thing will end up being -1. Okay. So if this can leak over, so this is what we want to avoid. So what we want to avoid. Okay. Because if P is too big, what's going to happen now is this term's going to be bigger than -1. Let's say if this is 1, this is bigger than -1. And then squiggle I mu, which is supposed to be 1, ends up being -1. And once that happens, then everything falls apart. Okay. So what this says something very important. So for sparse connectivity, meaning each neuron makes only K connection, Okay, connections. Capacity, the number of memories, is proportional to K. And the constant proportionality, let's say best case scenario, so P equals 0.138 K. So K is approximately equal to 1,000. And that implies we can only remember only 138 things. Okay, which is not very many. And so far too low to explain the actual capacity that we have. So this is a problem, right? So we go back to here. We wrote down, oops, next page. We wrote down some problems with the Hopfield network, and all our connectivity is a really serious one. So is this model dead? So it turns out that, so in the classical Hopfield model, so classical Hopfield model, so if you make the memories sparse, so sparse memories, so squiggle I mu equals +1 with probability F, -1 with probability 1 minus F, and capacity, so capacity proportional to K over F. Okay, so if you make F proportional to K over N, implies capacity proportional to N. So that was a fix that was pointed out a long time ago. The problem is classical Hopfield model. If you do something more realistic, this goes away. So F, oops, what's happening? So oops. Okay. So it turns out that for more realistic models, capacity really does scale as 1 over K. Really is proportional to K. And we'll see that in a little while. So a Hopfield model currently needs to, we don't actually know, we no longer have a good model for memories. So you might ask why I'm telling you about the Hopfield model. It's a classical model, and I think it gives reasonable intuition. I'll sort of give an idea of that near the end. This idea that neurons are preferentially connected together is probably really what's going on in recurrent networks. But it's a bit of an open question how we actually get high capacity. There have been networks that actually give you high capacity. Whether or not they use the brain, it's not clear. I'll send you the reference, but the papers are pretty hard. In fact, I barely understand some of them. Okay. So that was this was number 3. We're now going to actually look at number 1 and number 2. And these are actually going to be a pretty interesting exercises. They're going to give us a lot of intuition about how these networks work. And it's going to turn out that all the things we learned about randomly connected networks are going to be actually super critically important. Okay, so let's now consider sort of the first way you might want to upgrade these models. Instead of using continuous update, we're going to use something more realistic, which is DS. So DSIDT. Going to get rid of continuous update is some function instead of sine, which is a very sharp function. We'll have some smoother function. The sum on J of Jij 1 over n. We're going to go back to all connectivity because it's easier, but really we should think of replacing J by K. So the idea is that we shouldn't think of n as being very big, maybe 1,000. That's J. So now we have a continuous differential equation minus SI. And again, J is going to be our old friend, the sum on mu of squiggle I mu of squiggle J mu. So same model, but now because we have this function here, so probably generally, so you can think of f of x. We're going to use tanh x, but for now we'll leave it general. And that's very different. So remember, tanh x looks like this. So tanh x, this is tanh x. And that's very different than the sine function. The sine function looks like this. So sine. And actually what we're going to do is put in a beta here that controls the steepness. So beta goes to infinity. Beta goes to infinity. Gives us sine. Okay. But we won't take beta to infinity. We'll take it a little bit smaller. Okay, so now, because we have this tanh and not a sine, our old hypothesis that SI equals, so we can't guess SI equals squiggle I mu, because these SIs in equilibrium are going to be different from because the tanh are going to be different from plus or minus 1. But instead we define overlaps. So this is really how we should think about this. Mu equals 1 over n. It's now a function of t. Sum on J of squiggle I mu. Actually, sum on I of squiggle I mu SI of t. Okay. And that this is really this is normalized dot product. We can think of this as equal to squiggle dot s of t over n. Okay, and it tells us the extent to which this s lines up with this memory. Okay, if these are parallel, this is going to be large, and si is going to, and then if tanh s, this can't be bigger than n, it'll be less than 1. If this is nearly perpendicular, this is going to be very small. Okay, so it tells us the extent to which the memory, the activity lines up with a particular memory. And what we're going to do is write down dynamics for mu of t, and that's actually pretty easy. Let's go to the next page. So dmu dt, we use pretty much the same analysis as before, equals 1 over n, the sum on I of squiggle I mu times our function of 1 over n, the sum on J of the sum on mu, actually sum on summa nu of squiggle I nu squiggle j nu sj minus mu. Okay. Let's actually not skip steps. So remember dmu dt equals ddt of 1 over n, the sum on I of squiggle I mu si equals 1 over n, the sum on I of squiggle I mu dsi dt equals 1 over n, the sum on I of squiggle I mu. dsi dt is f of 1 over n, the sum on j, the sum on nu of squiggle I nu, squiggle j nu sj minus si. Okay. So this sum operating on the SI, that's what gave you the mu up here. Okay. And this term here is really just this term here. But now we can take this term and write it as squiggle, oops, squiggle I nu, or sum on mu, is rearrange the order of these things, times 1 over n, the sum on j of squiggle j nu sj, and this, of course, is m nu. So equations become dmu dt equals 1 over n, the sum on I of squiggle I mu, f of the sum on nu of squiggle I nu m nu. Okay, minus mu. So this is the equation we want to solve. It looks kind of complicated, but let's take a really simple case first. So a really simple case, so a simple case, just to get some intuition. So P equals 1 and F equals tanh beta. Okay, so we really have basically it's only mu. Mu is the only memory, so we can say mu equals 1. So we have dm1 dt equals 1 over n, sum on I of squiggle I1 tanh, and inside here we have squiggle I1 m1 minus m1. Okay, and the nice thing about tanh is it's an odd function. So so minus 1 times tanh minus x equals tanh x. Okay, we don't have to do that, but it's more complicated if we don't. But what that means is that we can take this squiggle 1 and put it inside here, right? The minus 1, whether it's a minus or plus, we get the same thing. We just get tanh, and what we get then is equals 1 over n, the sum on I of tanh m1. We forgot our beta. Beta is important. Beta m1 minus m1. And sum equals I equals 1 to n is just 1, right? So this is equals, we have dm1 dt equals tanh beta M1 minus M1, okay? And we all know how to solve equations like this. We solve, when we get differential equations, especially in 1D, we solve them graphically. And so on this axis, we have the M1. So this is 0. And this is tangent. Now beta really matters. If beta is small, so if beta is small, so beta small, actually less than 1, we're actually looking for, so solutions to the 45-degree line which is the red line, intersects tangent beta M1. So if beta is small, there's only one intersection, right? It's the only place to intersection, only place to intersect. So the only solution, is that M1 equals 0. So this doesn't really support memories. However, if you make beta big enough, all you need is beta bigger than 1. So this is beta greater than 1. And now you have these are memories. Patterns of activity that are going to stay there forever. And remember, to find stability, we just need the slope here. So we need to look at linearized dynamics. So these are stable and this is unstable. So even though we have an n-dimensional system, we've reduced it to a one-dimensional problem. Okay, and now we need to know about stability and the equations for that. So we have dm1 dt equals tangent beta m1 minus m1. And now we linearize, we let m1 equals some fixed point, m1 star plus delta m1. So m1 star can be, m1 star can either be this point, or that point, anywhere there's an equilibrium. And we linearize and we get d delta m1 dt equals tangent beta m1 star plus delta m1 minus m1 star plus delta m1. And we can Taylor expand as usual. So this is approximately equal to tangent beta m1 star plus tangent prime of beta m1 star times delta m1 with the beta in front minus delta m1. Actually minus m1 star minus delta m1. Okay. And because this is the fixed point, this and this, these are equal. So they go away. And we get d delta m1 dt equals beta. Derivative of tangent is doesn't really matter, cosh squared beta m1 star minus 1 times delta m1. Okay. And as usual, the sign of this term determines whether or not it's stable. Okay. So we look at the sign of this term as everything. So sign determines stability. stability. And at m1 star equals 0, m1 star equals 0 is this fixed point here at the origin, that one there. M1 star equals 0. So cosh squared of 0 equals 1. So beta, so we can now see beta less than 1 implies stable. Beta greater than 1 implies unstable. Okay. And you can actually, for the other fixed points, you don't need fancy math. You can just say, look at the slope here, which is all that matters. The slope here is less than 1. Slope here is greater than 1 and less than 1, as long as beta is greater than 1. So as soon as these memories appear, they're stable, and that's unstable. Okay. So that was the one memory model. This is a one memory model. Okay. And so I'm going to take a break now for 5 minutes. When I come back, I'll do the multi-memory model, which is, it's not really a lot harder. As usual, we're going to get some noise, which we have to deal with. The noise is a little harder to deal with, but we will kind of wave our hands. Okay, I'll take a quick 5-minute break. I'm here if you have any questions, and then we'll come back. Okay, so let's start up again. Let me see, where do we want to start? We're going to start with this equation here, except now with lots of memories. Let me save this to photos. Make sure it's saved. Yep. Okay, I'm gonna have to stop share, start share. An equation we're working with is dmu dt equals 1 over n, the sum on of squiggle I mu, and we'll use tangent again. The sum on mu nu, sorry, of squiggle I nu m nu minus mu. So as usual, we'll assume that mu is that memory mu is dominant. And there's a beta in here. Memory mu is dominant. And so we'll separate that out. So we're going to write dmu dt equals 1 over n, the sum on I. Okay, are we back? Sorry, I do not know what happens. Okay, sorry about that. So we're back to dmu dt equals 1 over n, sum on I of squiggle I mu, tanh of beta, the sum on nu of squiggle I nu m nu minus m mu. So we now have p equations instead of n equations, which is probably reduction, but there's still a lot of equations. So assume so mu large and m nu not equal to mu small. That's something we need to check when we're all done, okay? So as usual, we break things up. We write dmu dt equals 1 over n, the sum on I, the squiggle I mu, tanh beta, there was a squiggle I mu, plus beta, the sum nu not equal to mu of squiggle I nu m nu minus m mu. Okay, and now we can use the usual trick of taking squiggle I mu and bring it inside the tanh, right? Because the tanh is an odd function, and this is equal to 1 over n, the sum on I, tanh beta, sorry, squiggle I mu, m mu. Uh-oh. Beta m mu plus beta, the sum nu is not equal to mu of squiggle I mu, squiggle I nu m nu minus m nu. Okay, so if this term weren't here, we would be back to our one memory model. And we can ask, how big is this term? Okay, so as usual, these squiggle I mu and squiggle I nu, these things are independent random variables, right? These are a bunch of noise. So when we sum over nu, if p is large, this term here is approximately equal to, goes as the square root, there are p terms in the sum, so square root of p minus 1 times the average value of m nu squared. And this is, remember, the sum 1 over p minus 1, the sum nu not equal to mu of m nu squared. So it's the average of all these m nu's. So as long as they're small, then this is a good approximation. So it turns out you can kind of see that these things scale. So actually go to the next page. So let's take mu nu not equal to mu. So d m nu dt equals 1 over n, the sum on I of tanh beta m nu plus the sum, let's say rho not equal to nu, squiggle I rho, actually squiggle I nu, squiggle I rho, m rho. Okay, so now basically, so this is, if this is, it's all, we're not going to go into details, but it's all kind of consistent. If this is small, actually minus m nu. So if this is small, and this is random, remember, except m nu is large, m nu is large. But we're adding up n variables that are random. So this thing should scale if all goes well. This whole thing should scale. Scales 1 over root n. So implies that m nu goes as 1 over root n, m nu squared goes as 1 over n. So this shouldn't be super convincing, but if you are careful about it, you can convince yourself all this is true. And what happens is that this thing here is now proportional to n. So we end up proportional to the square root of p over n. Okay. And again, all we need is p much less than n. If we did, we're working the finite connectivity case, we do p much less than k. And what we get when all is said and done is d dmu dt equals tanh beta mu plus beta times some random variable, 8 of t. These things evolve in time. Call 8 of mu of t. Actually, let's put the scaling in. The square root of p over n, 8 of t, minus mu. So all it does is when we have our fixed points, so that's actually so we have our fixed points here. And all it does is basically early on, instead of going right to the fixed point, we might wiggle around a little bit. Oops, sorry. I'm going to change the color code. That's okay. So these are fixed points. And, we might wonder, man, I don't know what's going on. Okay. So fixed points. And because of these extra memories, we might be shifted a little bit. Okay, but besides that, not much happens. Okay, so what we have actually, so we've gone from discrete time to finite time, and that caused us to introduce these overlaps. Okay. So we still have the problem of there's no background. And that's the last thing we want to fix. And that turns out to be not so easy. But not so hard either. But this is actually, so now we've considered a very, very abstract model. What we want to do now, though, is go back and link it up and make contact with a randomly connected network. Okay, because it's really we have no random connectivity here at all. We've just included this complete structure. So now we're going to couple. We're going to say, okay, what happens if we start with random connectivity and we add structure? So we're going to consider a model like this. So remember, let's go back to my favorite equation, tau. Actually, I don't want that color. So tau dvi dt, vi is now back to voltage. Voltage equals minus vi minus E leak, the leak memory potential, plus the sum on J of Wij E, we have this new Ej, plus the sum on J of Wij new Ij. So of course the Wij's, these things are, so these are negative because they're inhibitory. And these are positive. Okay. And we're going to add structure to this. So what we're going to do is going to take these weights. So Wij goes to Wij random, like we had before, plus Jij. And this is going to be structured like Hopfield networks. But we're going to consider something a little more realistic than plus or minus ones, which you could do if we wanted, but we're going to consider something more realistic. And that is, so Jij, we consider all connectivity, although again, we should really think of this as n is not so big, is 1 over n. Tell you what these terms mean in a second, f1 minus f times the sum on mu of eta I mu, eta j mu minus f. Okay, where eta I mu equals 1 with probability f and 0 with probability 1 minus f. Okay, this is it's similar. It's random again, but it's kind of a different structure. So what we have here is basically, so for particular mu, so this is a fraction f of the neuron. So this is our whole population. This is a fraction f of the neurons. So f might be 10%, 20%, as we'll see, it can't be too small. So all the neurons over here, have a to I mu equals 1. Okay, so if you look at here, Jij is positive. It's 1 here and 1 minus f. So the connection strength here is basically so sort of these things excite each other with a strength proportional to 1 minus f. Actually put a beta in here. I don't know. Do not know why that happens. Okay. All the neurons out here, for all the neurons out here, a to I mu equals 0. Okay. And because it's 0, this is a minus sign. These are negative weights, right? So this is 1 times minus 1. So here, these things inhibit each other, inhibit the ones that are going in here. Minus f. So their strength is minus f. Okay. So the reason we did that, the Hopfield network was kind of weird. If we go back to this picture, there were actually 2 fixed points, one up here and one down here. And that's because of the squiggles were plus or minus 1. So in the Hopfield model, we basically had a picture like this. These neurons excite each other with a plus. These were a plus. And then across here, there was a minus. And then in this direction, there was a minus. Okay. And what that meant is you could either have either these neurons could all be active, and these at +1, these all -1, and that works, right? The +1s excite each other. The -1s excite each other even when they're turned off. Okay, or you could have all these active and these turned off. Okay, and that's not really something we want. It doesn't quite make sense for real neurons. So for real neurons, we have this more realistic thing in which basically what we're expecting is all these neurons can have elevated firing rate. And that's what's going to correspond to memory. And of course, this is some random fraction. A different random fraction would be partially overlapping. And the smaller the f is, the smaller the probability of an overlap. Okay, so that's a setup. And so now we're going to actually skip lots of steps and use what we've done before. So we're going to write down an equation that's going to look something like this. I'm going to be a little bit loose with notation. So what do we expect? Oh, so one thing to notice is that I added structure only to excitatory neurons, not to inhibitory neurons. Okay, and you can add them to inhibitory neurons as well. It's just I didn't for convenience. That's really the only reason. Okay, so now we're going to write down our firing rate equation. So we have something like tau e d. What's happening here? So we have tau e d nu e I dt equals psi. We're going to use firing rate equations. Psi e I. We have WEE, some average firing rate nu e, minus, let's say WEI times average inhibitory firing rate. And then we have plus 1 over n f, 1 minus f, the sum on j of, actually, let's just, for now, the sum on j of some structured connectivity. J, I, j, nu, e, j, minus nu, e, I. So it's a set equations you've seen before, we just added structure. It's all we've done. And we have equations for I, tau I, d nu I, dt equals psi I of w, let's say wi nu e minus wii. So this is very similar. Before we actually were in some sense more general. So this is a more specific model. So before we had, so in the old days, so previously, we wrote psi ei of nu e and nu I, and psi I of nu e and nu I. But so we just adding in the weights. It doesn't really matter. We didn't have to do this, but it's kind of easier to see things. And certainly what we definitely want to have is the WE and this thing added together. Okay, this is from the average firing rate, and this is from the structure. Okay, so we're going to make an approximation. It's really mainly for convenience. So approximation tau I equals 0. So fast inhibition, or infinitely fast inhibition. Okay, doesn't actually reach 0, it just that goes there. It has to be sort of much smaller. We really just need tau I much less than tau E. And if tau I is really small, what this implies is that nu I is basically instantaneously set to of WIE nu E minus WII nu I. And we could have, if we wanted to, had this equal to, sorry, this is a, if we wanted to, we could have written this. It doesn't really matter. Psi I of nu E nu I. This is kind of a detail. And so that basically, we can solve for psi I and write implies psi I equals some other function, it's called psi tilde of nu E. Okay, and it's important to understand what that means in terms of our null-Klein picture. So here are null-Kleins. I made these green. Okay, so fast inhibition, let's label the axes. So nu E, oops, nu E, nu I. So fast inhibition means inhibitory neurons stuck on this line, right? This line is by definition nu I equals psi I. I'll go back to writing it like this. Okay, that's how that line is defined. So what that means is we're stuck on here. And this is important. That means if nu E increases, so if we're sitting here, if nu E increases, inhibition goes up and drives the network in this direction. Okay, so actually I will, so let's say we're sitting right here. So we're sitting right here. So we increase nu E. So nu E somehow goes up to here. So increase nu E. Actually, better pictures. We start here and we increase nu E. So we go to there. Immediately, we're pulled up to here. Okay, with the fast inhibition, and then we're pushed in this direction. So basically, oh man, why does that happen? So basically, we are goes up, and we basically hang out on this line. So we're pushed back. So basically, fast inhibition really means that d nu E tau E d nu EI dt equals, I'm going to write it as some other psi of minus nu E plus the sum on J of J I J. I'll put a weight in here. There's some weight, some effective weight. Minus W E nu E J J nu E J minus nu E. So this is basically in excitatory neurons. Are now inhibitory. So this is non-trivial, right? We start with this picture of null clines, and these null clines coupled with fast inhibition means excitatory network neurons are actually inhibitory. Okay, and they're pushed back toward an equilibrium. And there's some equal. If this term was zero, so nu E, if this term is zero, there's some equilibrium firing rate that sits right here. As in the increase in firing rate, we'll push back. So this makes things very, very stable. Okay. And if you remember correctly, that was part of our analysis. Since if tau I is small, everything is very stable. Okay. So this is our model we're going to work with, and we're going to go back to this J and work it out. And I can actually remember the effect of all the other memories is just to add noise. So I'm going to consider the one memory model. Okay. So we're going to do this, and we're going to consider the one memory model. So all right, this is tau E d nu EI dt equals some function of minus WE nu E is, remember, the average firing rate, plus beta over NF 1 minus F, the sum on J is an eta I, eta J minus F times nu EJ minus nu E. Okay. So there are now actually two relevant quantities here. There's nu E, which is 1 over N, the sum on I of nu EI. And there's this overlap term here. Same overlap we had before, which is sum on J of eta J minus F nu EJ. So we're going to find the overlap. So M as our overlap is defined to equal 1 over N F 1 minus F. That NF 1 minus F is just for convenience. Sum on J of eta J minus F nu EJ. Okay. And if you go back to our picture that we had before, the overlap, so our picture is right here with only one memory. Our overlap is going to be positive if these neurons have an elevated firing rate. And otherwise, if these neurons and the background neurons have the same firing rates, overlap is going to be basically zero. Okay, so Battery's running out, but it should last. So this is basically, so 0 if all neurons have about the same firing rate. And positive if neurons with eta j equal to 1 have elevated firing rate. Okay. So with this definition, basically what we've done is replace this quantity here with m. Okay. And we want to write down a differential equation for m. So we write down tau e, just like we did before, dm dt equals 1 over n f 1 minus f, the sum on j of eta j minus f nu ej, which is psi of minus we nu e plus beta m, plus beta eta I m minus nu ej. So I missed, this is a new EI. Okay. So first of all, this sum on J operating in this term here, it's just a regular old M. So the second term is M, that's the easy one. So this is equal to 1 over NF 1 minus F, sum on J of eta J minus F, psi of minus WE nu E plus beta eta I M minus M. Okay. So now this is where things get a little bit tricky unless you're used to doing this. So if you look at this sum, so there are, so NF terms have eta I equal to 1. And those terms, so, and for those terms, you get this factor of 1 minus F. So for those terms, you get psi. So how many terms are there in there? There are, first of all, so there are n terms, F. You get this factor of, because eta j is 1, you get a factor of 1 minus F. And we divide this by NF 1 minus F. And because eta j is 1, we get psi of minus WE nu E plus beta M. Okay. We also have N 1 minus F terms have eta I equal to 0. Remember, the problem that eta I has 1 is 1 minus F. And so this gives us, it's going to have N times 1 minus F terms. You get a factor of F from here. Actually, you get a factor of minus F. So you get a fact, because eta is 0, you get a factor of minus F from here. So there's a minus f, so there's a whole barrel minus sign, and we divide by n. F, 1 minus f, and things cancel, and we get psi of minus w e nu e. Okay, so it's kind of dense and complicated, but basically we just take this equation. We said a to j equal to 1 with probability nf, and 0 with probability 1 minus nf, and that gives us the sum of this term and then minus that term, because when a to 0, you get a minus sign. And when you put all that together, you get dm dt equals psi of minus nu e plus beta m minus psi of minus nu e minus m. Okay, so that's the updated equation for our overlap, which is a nice simple equation. So what about update rule for the average firing rate? And we're just going to average this term. So that's actually easier. So we have tau, actually there's a, sorry. There's a tau e here. So we have tau e d nu e dt equals 1 over n, the sum on I of psi e minus nu e plus eta I beta m minus nu ei. Okay, so this term again, there's a fraction. So this is a fraction. F of these have eta I equals 1. So f is psi e of minus nu e plus beta m. And a fraction 1 minus f fraction 1 minus f has eta I equal to 0 of minus nu e. And then this second term is average e. So we get, what we get is psi e of minus nu e plus f psi e of minus nu e plus beta m minus psi e of minus nu e minus nu e. Okay, so it's quite, oops, couple mistakes here. First of all, we need the e. More important. Okay, that's right. So this is kind of nice, right? This term here is exactly the same as the term that shows up here. Okay, so we've coupled the background. So what we've done, so we've done a fair amount of algebra, but things should kind of make sense. So we coupled background firing. This is just nu e, the average firing rate, to the memory. Okay, so we have two equations, two unknowns, which now we should be able to solve. This is why these null lines are really, really useful. They show up far more often than you'd expect. Okay, and so basically we have to solve them. I'm going to solve them graphically. There's 2 minutes. So I'm going to focus only on this term. So I'm going to plot. So I'm going to plot on this axis m, and this is our line, 45-degree line, m equals m. And what I'm going to plot in blue is going to be psi of minus nu E plus beta M minus psi of minus nu E. Okay. And that is always 0 when M equals 0. And I'm going to draw a picture like this. Depending on the size of beta, it's going to have different shapes. I'm going to draw it like this. Okay, so this is a plot of the right-hand side and the equilibrium. So this is an equilibrium, equilibrium, equilibrium. Okay, so these are equilibria. And what it looks like is, so this one, so this one is stable. So this one looks like it's unstable. And this one looks stable. Okay. And when we do the analysis more carefully, what we're going to find is it's possible to stabilize this equilibrium, just like we stabilize the unstable branch of the excitatory null. So all the null analysis we did for the randomly connected networks, assuming you absorbed it, which it's tough on the first time around, is going to be useful here. So that's what I do next time to finish up Hopfield networks with a background, and then we'll go on to line attractor networks, and then deep networks, and then a little bit of learning. Okay, so I'll be around here for another 5 minutes or so if you have questions. I'm going to save this to photos because my battery's about to run out. If I suddenly disappear, that means I actually did run out of batteries. Okay, good. We have all the photos. Okay, thanks, gang, and so I'll be here for a little while, like I said, and then I'll be back again on Monday. And by the way, I'm going to put all sorts of papers online. They're mainly pretty hard, but if you ever want background reading on all this, it'll be there. Okay, thanks.